Okay, good morning.
Sir.
We will continue our discussion, but before that, I want to ask you on the proof. What's your idea to proof number 3? This is false. It is false, so what's the proof?
Try different combination of number.
No, that's not how we do it.
Different squares. 3 times 3 together. Itu
Alfred.
nggak bisa bro, betul?
Sorry? Okay, he said the eigenvector. Okay. Eigenvector is the key. Okay, let's see. The statement says like this: if a plus b times x equal to lambda x, then then we have axa, lambda a xa, and b xb, lambda b xb, where lambda is equal to lambda a plus lambda b. Okay, so this statement is saying the same thing as this. Okay, yeah, even actually it is if and only if condition. If we have this, then we have this one. Okay, we will prove it this way. I will continue from here. Yeah, I will continue from here, where step by step, slowly. So I will write that a plus b x lambda x. So in this case, lambda is the eigenvalue of a plus b. Okay.
Yeah.
And then let us multiply a and x, and also bx to the lambda x. Yeah. So let's say that if this is true, yeah, this is true, and then this is one of the eigenvector. Let's say if we say this is lambda a times xa, or lambda a times lambda a times x, and then this is lambda b times x is equal to lambda times x, then this is true only when the x for the a and x for the b are the same. Yeah, we can say this so that lambda a plus lambda b x, this is only true when the eigenvector for a and b are the same for that particular lambda. Okay, because since xa is not the same as xb, this is false. Okay, the x for a and x for b, they are not necessarily the same. Okay, so we cannot obtain the result. So the condition for this to be true is that eigenvector for a and b must be the same. Okay, can that happen? Yeah. In what condition so that eigenvector for a and b to be the same? In what condition?
Matrix A and B is the same.
Same matrix. Okay.
Okay.
If they are not the same, what kind of matrix that can achieve this?
If one of them is identity.
Not identity in general. In general, identity is what?
Is basis for the
A more general form of identity is what? Identity is a special case of a matrix, right? But if we take the general form of identity matrix, then it becomes what? Diagonal matrix. So if A and B are both diagonal, then this is true. Okay?
If one of them is diagonal, it's the false.
False. Both of them must be diagonal. All right. Let's move on. Any question on that? It will not be appear in exam, I think. No. Just a discussion, yeah. Now we will discuss about eigenvalues for symmetric, skew-symmetric, and orthogonal matrices. They are special matrices, and so they will have a special property on the eigenvalue. Okay. To review again, symmetric is we transpose it, it becomes itself. Okay. The transpose it itself, then it is symmetric. Skew symmetric means if you take the transpose, it becomes the minus of that matrix. Orthogonal, the transpose is the inverse. Okay. In the subsequent slides from Wayne Hacker, R is denoted for symmetric matrices, S skew symmetric, and Q for orthogonal. Just a naming. Okay. So let's say you find out A is S, let's say, then A is skew symmetric. Another review on skew symmetric. Skew symmetric must have 0 to be the diagonals. Yeah, 0 is the diagonal entries for the skew symmetric matrix. Okay, so this one is not skew. The skew symmetric has two properties. The first one is that diagonals are 0, and then the anti-diagonal have different sign. Yeah, one positive, one negative. So although this one have positive in here, negative in here, same number, yeah, the diagonals are not 0. So this is not skew symmetric. Yeah, just to review. Now these are the eigenvalues for symmetric and skew symmetric. The easiest one to remember is that symmetric matrices have real eigenvalues. Always real eigenvalues, cannot have complex. What if it is not symmetric? What's your idea?
The root can be
The eigenvalue
can be complex.
can be complex, but must it be complex or can also be real?
Can also be.
Yeah, can be real, can be complex. Okay. If it is not symmetric, can be complex, can be real. Yeah. Another thing for symmetric matrix we will discuss later. That's about the eigenvector of the symmetric matrices. But this is for eigenvalue first. Okay, the next property is for skew symmetric matrix. It's either pure imaginary or 0. Okay, so what does it mean? The real part of the skew symmetric matrix is always 0. The real part. Yeah. Eigenvalue, real number is a complex number where the imaginary part is 0. Am I correct? Yes?
Can you repeat? The
Real number is a complex number where its imaginary part is 0. Yeah, okay. So in this case, for skew symmetric matrices, eigenvalues are complex, but then the real part is always 0. Okay, so it's either pure imaginary or just 0. So where does if I draw a complex plane, this is a complex plane, yeah? This is real axis, imaginary axis. Where does the skew symmetric matrix eigenvalues lie? Where? 0 real part. Huh? Here?
Yeah.
Real part is 0, no?
Imaginary.
This one, yeah? It stays here. It's either 0 here, all of them here, or it's spread. Okay. So now if I ask you, if we have 2 by 2 matrices, Where do you think the eigenvalue will lie? Is it zero, pure zero, or will it be pure imaginary? Only two choice. Why pure zero? Yeah, this is skew symmetric. Either pure zero or imaginary. Yeah.
Could be minus 2 kayak plus I.
Yeah. In fact, it will be complex with zero real part. Okay, for this one. If you have 3 by 3 matrices, minus 1, 1. Okay, this is 0. Then if it is like this, one of them must be over here. One of them, because if they are complex, they will have complex conjugate. Okay. So the possibility for this is that one of them is in the origin, and the other two could be over there, or the other two could be here. All of them, all the three are there on the origin.
There will be like one will be 0 and the other two will be.
It could be imaginary, or it could be all 3 0.
Oh.
Yeah, it can be.
For skew symmetric, even if the diagonal is 0, as long as the anti-diagonal, if you transpose it, it's still inverse. The negative, is it still correct?
Say it again. You transpose it, it become inverse.
Even if the anti-diagonal has a value.
This one?
Yes.
Yeah. Does it still skew symmetric? You mean? Yes. So we have 0 in the diagonal, and the anti-diagonal have different sign. This is skew symmetric.
So there will always be one that is 0, but we don't know if there will be imaginary.
If it is odd size, yeah, 3 by 3. If it is even size, then they could be all imaginary. Yeah, because when it is imaginary, you will need complex conjugate. Okay, complex conjugate. Let's say you have an eigenvalue of 0 minus 5i. We cannot have this one alone. Cannot. You will need another eigenvalue as the pair, complex conjugate pair. Okay, so if you compute an eigenvalue and you only find only one of this in this kind of format without the plus 5i, you make a mistake. Must be, you make a mistake. Okay. Okay, the third one is about the orthogonal matrix. Yeah, orthogonal matrix has the transpose to be its inverse. Yeah, the transpose is in inverse. Okay, that's orthogonal. What about its eigenvalue? Its eigenvalue have absolute value of 1. Okay, the absolute value of the eigenvalue is 1. What's the possibility of that? The possibility of having absolute value of 1. What's the possibility? If it is real, it's always 1. Yeah. If it is not 1, then it must be
0.
complex. It must be complex.
Not it be 0.
Yeah. Orthogonal matrix, absolute value 1. Yeah. Where does the eigenvalue lie? If the absolute value is 1.
Real.
Okay, what does it mean by absolute value 1? If you have a vector, absolute value 1, then it means the length is 1. Okay. So how do we get a vector that has length of 1? Any kind of vector has length of 1, then where does they lie? Where? No. XY.
Plane.
XY plane, yes. Where?
Quadrant.
Huh?
First quadrant.
No.
From
Alfred, your idea. Come on. You went to Singapore, right? What did you learn in Singapore? Nothing, huh? Sorry.
Voila.
Okay, what do you think?
Unit circle.
Correct. Wow, that's a good idea. His answer is correct. It's unit circle. Okay. So orthogonal matrix eigenvalue is here. Yeah. It can be -1, +1. Okay. It can be here. Okay. Plus minus I. It can be here also. Okay. If it is here, then the friend is here. Yeah. So eigenvalue of orthogonal matrix lies on the unit circle. Okay. Isn't it nice? Yeah, it's special matrix, so it has a special place for its eigenvalue also. Okay. Yeah. If let's say you want to make an improvisation using mathematics, try to make a matrix where the eigenvalue lie on some kind of special shape. Let's say in a box. Can you do that? I challenge you. Eigenvalue of my matrices lies in a box specified by this formula. Wow, that's very nice. Isn't it nice? You will be happy when you reach. Wow, I can create a matrix has eigenvalue in this kind of region. It's nice. Yeah, just like this one. Okay, it only lies here. Cannot
So
move to the left to the right.
Unit circle.
Unit circle.
The limit.
Does it lie here?
Yes.
No.
No. Berarti bukan the limit dong.
It's not the limit. It's always in the unit
circle.
at the unit circle.
Yeah.
Yeah.
Garis.
On the unit circle is on the line. Yeah. Nothing more, nothing less. Okay. So this is the proof, yeah. The proof to show that the eigenvalue lies on the unit circle. That's the absolute value is 1. Okay. I don't think you will care about proving it, or do you care? You don't care? Or you want to know how we derive it? Really? Not really useful to answer the exam, but it is interesting as an engineer. It will be interesting to know. Okay. So you first get the quadratic format of this orthogonal matrix. Yeah. If we have q times x and x is the eigenfactor, then we will have lambda times x. Okay. So we want to obtain the lambda based on this dot product of that factor. So we multiply qx transpose times qx, and so because of the transpose, we flip the order. Yeah, it becomes like this. And the special property of orthogonal matrix q transpose q identity. Okay, so we get this. So it becomes x transpose times x. And you know that x transpose times x, it is the square of the norm. Okay. You know how to get the norm of a matrix? The norm is square root of the dot product of itself. Yeah. Yeah, norm is the square root of the dot product of a vector by itself. So if we remove the square root, then we get the norm, then square it. Okay. And so each of these consists of lambda times x. Yeah, because lambda is the eigenvalue of the q. Okay. The normal, that's the usual definition of ax equal to lambda x. Now we have q in there. Q is our orthogonal matrix. Yeah, so we replace with lambda x. Yeah, now lambda x is here, lambda x also there. Okay, and so we have lambda square and then x transpose times x. Okay, yeah, because this must be the same with this one, it must be that the lambda square has to be 1. Okay, the left side must be the same as the right side, so lambda square has to be 1. That's the result. I noted this is 1 minus 1. This is I minus I. Okay, this is the result of that. Any question on this? Alfred, Michelle, Michael, Brian, yeah, Johan. Okay, now I get it the name correctly, yeah.
Can it be like real, so it's x, y plane?
Real?
Can the orthogonal eigenvalue can be either real or not?
Yeah. If it is real, then let's say this is 1 minus 1.
Yeah.
That's the only real eigenvalue.
Oh.
Okay. Other than minus 1 and 1, it will be complex. Yeah. Yes. Or in here, it has real and imaginary part, right? In here. There also. Johan? Where? Here. Yeah, this one we don't need the transpose. Yeah. So x transpose times x. Yeah, the lambda you got. This is scalar. So it's a typo here. Yeah, there is no transpose there. Following the qx, it has to be lambda x. Yeah, lambda is a scalar, so you move it to the left, become lambda square. X transpose times x, it becomes this. All right, let's move on. Okay, answer number 4. Can any matrix be written as sum of symmetric and skew symmetric? Can we do that?
Sum.
The answer is true. The answer is true. Now you just have to think how can that happen. The answer is true.
Any matrix.
Can A be written sum of symmetric and skew sum?
Like, can any
Matrix can A be
If A is symmetric, yeah, A will be equal to A transpose. If it is Q, it will be A transpose is the minus A. Okay. So,
oh, minus A times A.
no.
Yes, there's nothing to do with identity.
We can write down. Let's say we want to write A. A is equal to the sum of R plus S. Like that. So how do we do that? Symmetric matrix I can write down as half of A plus A transpose. When you have this, then this will be symmetric. What is the transpose of A plus A transpose?
transpose of A.
Okay, A plus A transpose You transpose it. What is it become?
S times 2.
Is it the same with this? Is this the same with the original one?
Yes.
So it is symmetric.
Yes.
Oh,
You divide
So-
it by
why half? Yeah.
Yeah, I'm doing half because I want to do half also here.
Oh,
Okay.
so the same thing with us.
Yeah, and any matrix, square matrix, yeah, when you do this, then this will become a symmetric matrix. Okay. Yeah. Okay. Now what to do with the skew symmetric? I will write it down as half A minus A transpose.
Which one is Q?
The skew one is the R. R is the skew. Yeah, I'm saying that this is a skew symmetric matrix. So if I do the transpose, it becomes what? Huh? A transpose minus A. Okay, so this is minus of that. Do you understand? Now, do you remember the definition of skew symmetric? The transpose is minus of itself.
Yeah.
Okay. Now I'm doing the transpose of this matrix. It becomes minus of the original one, right? So this is skew symmetric. Huh? Do you think I'm cheating? It's like cheating, right?
Yeah.
That's what how mathematics work. It's like cheating.
Dapat dari mana ya?
Yeah, it's something. Oh, it's coming from somewhere. But that's the fact. You take the transpose, it becomes the minus of the original one. Yeah. Let's say this is B. You take transpose, it becomes minus B. Yeah. See, this is the skew, right?
Oh, yeah.
When I write this now, yeah. Yeah. Now B is A minus A transpose.
B is A.
Yeah. Take some time, yeah. Okay, take your time. Okay. Still any doubts, Michael?
Sir, when you transpose the minus A, it becomes minus A. It becomes A.
Minus A.
Oh, so you transpose it again,
Yeah, A transpose, you transpose it, become A.
yeah?
Yeah. The minus sign is still there. Yeah. Now what's the result of this?
Yeah, itu.
So this is half A minus half A transpose plus half A plus half A transpose. Which one I can cross?
The transpose.
This one I can cross, so it becomes A. Right, so I can do that. Okay. Now, is A and A transpose the same or not?
Yes.
Are they the same? A and A transpose, are they the same? No. We are not talking, the A is not symmetric.
Oh, any matrix ya?
It is any matrix.
Okay. Yep. Any matrix, bro.
Any matrix, yeah. If they are symmetric, then they are the same. But still, it will be gone, yeah. It will be gone. Whatever matrix we have, this a term and that term will be crossed out. We only left with the A. Any square, yeah. Any matrix A, sum of No, the problem is wrong. Any square matrix. Okay. Yeah, because symmetric matrix cannot be applied for rectangular matrix. Yeah. But the answer is true in this case. We are saying that it is. You see, in the beginning when you say it is symmetric, then it is square already. Okay, not a rectangular. What it means here is that any square matrix. But good point, yeah, Brian. Good point. It is for the square matrix. And then I think in that problem it is not stated square or rectangular because we are discussing eigenvalue. Okay. In chapter 8 we are discussing eigenvalue, and all matrices involved here are square. There is no rectangular matrix. Okay, all of them are square. So all matrices that you see here, it is all rectangular. Square. All of them are square. Okay. So the question that you have here, any matrix, it is referred to the square matrix. Okay. That's, I think, probably the reason why when hacker do not write any square matrix. Okay. Okay. Problem number 5. The only diagonal skew symmetric is the zero matrix.
The only diagonal is the zero.
Yes. It's true, yeah. It's true. It's true.
Iya kan harus no.
Yeah, because the diagonal has to be zero. Problem number 6. Symmetric cannot have eigenvalues that are zero.
Yes. Cannot have an eigenvalue that are zero.
Yeah.
Cannot. Yes.
False. Yeah, that's correct. It's false. You want to prove? Do you want to prove? Okay.
Sir, isn't the matrix that cannot have zero eigenvalue is the orthogonal? Is that right?
No, orthogonal
Can be.
eigenvalue can be zero. Can be zero. Orthogonal.
Oh,
This is symmetric, right? Yeah. What's the eigenvalue of this?
zero.
0 and 0. Okay. So symmetric can have 0. Wow, you're so surprised. Why? Well, what's the property of eigenvalue for symmetric?
It can be.
Huh? Yeah, any real number. Yeah, it's real number. Is 0 a real number? Yes, it's a real number. So when your exam is 0, it is real. No, I'm just repeating the statement. It's a real number, right? So when you get 0, that's a real number. Yeah. If let's say you get you do an exam and then I give you 100i, that's imaginary. Yeah. We are playing with the terms, yeah.
Negatif number nggak ada?
Sorry?
Negatif number. Kalau dikasih negatif 10. Walah. Lu bisa capai lebih jauh dari nol itu habis banget.
Okay.
What the
When you do problem 1 point F, if you answer you get -10, let's say like that, yeah. Your answer correct, you get -10. Yeah. Number 7. At least one zero eigenvalue?
No.
No, yeah, that's correct.
Can either be imaginary.
If it is 0, then both of them must be 0.
Yeah.
Okay, it cannot be 1. If it is 2 by 2, if it is 3 by 3, then it's correct. Yeah, for 3 by 3 it is correct. Who don't get it? All of you get it? Alfred, do you get it? Number 7, do you get it? This is false, number 7, yeah. Number 8, 0 is both symmetric and skew symmetric. Is this correct? Huh?
The zero matrix
Why?
is both asymmetric.
Is it 0 is this? This is 0.
Zero mark?
Yeah.
No.
Huh?
The zero matrix.
Wait. See number 5. The only diagonal skew symmetric is 0 matrix.
True.
It's true, right? So this is true also.
Only diagonal.
Say that again. Not necessarily. This is skew symmetric. Yeah. This one. This is not symmetric. This one. 0, 2, minus 2, 0. But this one is at the same time symmetric and also skew symmetric. This one. Didn't you say this true just now? It's you, right? Where do you get the inspiration to answer this is true? It's ghost that send you the signal. True. Yeah. So the anti-diagonal term for skew symmetric can be 0. Of course. Don't limit the number to be has to be plus and minus. Yeah. One value you get plus 0, the other one is minus 0. It's 0 lah. What is plus 0? It is plus 1 times 0. Minus 0, it's minus 1 times 0. So they are 0. Okay, identity matrix, is it orthogonal? Yeah, the orthogonal matrix is transpose, it is its inverse, yeah. What do you get when you multiply identity with identity? It becomes identity again. What is the transpose of identity?
Inverse.
What is identity matrix? Yeah. Right. Any questions so far before we go into the next topic? No? Okay, let's move on. This topic is even more interesting. Yeah, we are doing diagonalization. We are still discussing square matrix. Yeah. Okay, now about positive definite matrix. What I want to say about positive definite is this. Yeah, this is the definition for positive definite. If it is positive definite, then and this is a scalar, yeah, scalar, not a vector, not a matrix. X transpose times A times X, it is scalar. Okay, and then this applies for all X, and X cannot be 0. Yeah, of course X cannot be 0. And there is another definition which is called positive semi-definite. As the term says semi, then this has an equal sign in here. Okay, X non-zero. So for this type of matrix, there exists non-zero X which can result this. Yeah. And it must be that for this matrix, this is a singular matrix. Okay. Singular matrix can have this.
They have to be singular or non-singular.
For non-singular, cannot. Okay, because X has to be inside the null space of A. A matrix will have a null space if it is singular. Yeah, do you remember?
Yeah.
Remember this? Yeah. What about this? Does all non-singular matrix? The answer is no. Yeah. A must be non-singular, but not all non-singular, because some of them would have. Sorry. Some of them could result in less than 0. Okay, this is negative definite. But we are interested in the positive definite. Okay. Okay, yeah. And then this format is called as the quadratic form. Quadratic form. An example of this. What's the example of that positive definite? If we have a diagonal matrix like this is positive definite. Let us multiply with any kind of factor. What do we get? This is x1, x2, yeah, correct? Then it 2x2, sorry. Then it becomes x1 square plus 2x2 square. Okay. For any non-zero x, this will be positive. Am I correct? For any non-zero x. Can you see that? You mentioned any x. You want it x to be negative? Negative 5. You square it, positive, right? In here, negative 8. You square it, positive also. So for any kind of x, you will get positive. Okay. An example for this. Example. Let's say we have this matrix. What do we get? x1 minus x2. And then in here, minus 2x1 minus 2x2. Sorry. I have to do this x1, x2, x1 minus x2. This is 2 minus x1 plus x2. Okay, so the result is multiply by that x1 square minus x1 x2, yeah?
Yeah.
And then this one times this minus 2 x1 x2 plus x2 square. Okay, so we have x1 square plus x2 square minus 3 x1 x2.
So for all rank, it has to result in scalar.
Wait. Am I getting it correctly? 2 square. Oh, this is 2, yeah? So this is 2. Yeah, for all kind of x, not for all kind of x, yeah. So this means that for some x, this will be 0 for some. But for any other x, it will be positive. What is the example of x1, x2 that will make this to be 0?
0.
If you put x1 to be 1, x2 to be 1 also, what do we get? 0, yeah? So this is X that can make the system to be 0 in here, the quadratic form to be 0. But for any other X, it is positive. Okay. So let's move on. Oops, what's it? Oh, we have a theorem. Basis of eigenvectors. Distinct eigenvalue. Distinct means you have different value of the eigenvalue. Okay. If it is distinct, then it has a basis of eigenvectors. So distinct is a guarantee for you to get eigenvector that are linear independent. Okay, what does it mean? And anyone can try to interpret this theorem?
If eigenvalues
This is a upper triangular matrix. What is the eigenvalue here? 1 and 5, correct, yeah? So lambda 1 is 1, lambda 2 is 5. So this is distinct eigenvalue. If it is distinct, then your eigenvector will form a basis for Rn. Do you remember what is basis? A set of vectors is a basis if they are linear independent and then they span the Rn. Okay. If it is 2 by 2 like this, then span R2. Okay. Yeah. So we take understanding from chapter 7. What if I have this one? What's the eigenvalue? What's lambda 2? 1 also. It is not distinct. It is not distinct, yeah. They are the same. 1 and 1. So when it is happen, there is no guarantee that you will have a basis of eigenvectors. In some cases, you can still have basis of eigenvector. Okay, this is in fact a Jordan block, which I don't know whether we will discuss that or not. Jordan block, yeah, not Michael Jordan. Okay, this is a diagonal matrix. What's the eigenvalue? 1, 1. Okay, same eigenvalue, yeah.
Yeah.
But this one, even though it is distinct, the eigenvector forms a basis for the R2. Do you want to give a try? Okay. The first eigenvalue, yeah, 1, 0, 0, 1. The first eigenvector is this. Is this correct? Yes or no? Sorry. This is 1, 1, 0. Sorry, 1 and 0. Okay, so the first eigenvector is 1 and 0.
Yeah.
Okay, let me get the second eigenvector.
Yeah.
1, 0, 0, 1, and I have 0, 1.
Yeah.
Correct?
Right.
Yeah. So this vector form a basis for R2, even though they have the same or repeated eigenvalue. Okay. So this is a bit constraining actually, yeah. But this one can guarantee that we will have basis for Rn. A more general theory is that if you have distinct eigenvalue or you have repeated eigenvalue with Jordan block order of 1, yeah, there is no Jordan block again. Repeated, but there is no Jordan block. Then you will have a basis for eigenvectors. Yeah. Symmetric? No. Distinct eigenvalue. Yeah, we are talking about distinct eigenvalue. Yeah. This is symmetric, but this is diagonal. So not all symmetric can do this. Okay. Yeah, the hardest part is when you have a repeated eigenvalue and then you have a Jordan block. Eigenvector will not be linear independent. That's the problem. Wah, sleepy ya. Yesterday when the control system class was sleepy, I asked them to stand up and then do stretching. Do you want to do that? Anyone doing sport lately? Can you lead the stretching movement? Just 1 minute lah, 1 minute lah. Come on, Sean.
Yeah.
Just 1 minute, 1 minute.
Right, for your hands start with this.
Okay, let's stand up. Everyone stand up. Yeah, stand up. Oh. Okay.
1, 2, 3, 4, 5.
Okay.
1 plus 4 is 5.
Wow, this is nice.
1, 2, 3, 4, 5.
Okay. Okay. Nice, thanks. Okay, let's sit down again. Okay, the next one. If it is symmetric, then it has orthonormal basis of eigenvectors. If it is symmetric. Okay, we are not talking about distinct eigenvalue here, but we are talking about orthonormal basis of eigenvectors. Okay, so when you are symmetric, when you have a symmetric matrix, there is a possibility that you will have repeated eigenvalues. Yeah, eigenvalues may not be distinct, but the eigenvector is a basis. Not just a basis, it is orthonormal. You remember what orthonormal?
Orthogonal, but
orthogonal, and also the length is 1. Yeah.
Oh, yeah.
That's orthonormal. Orthogonal and also the length is 1. And for sure, these eigenvectors span the Rn. Yeah. They are linear independent. So symmetric is a special case of matrix. Now you see why symmetric matrices are special. Yeah. And it's also hard to get. I mean, yeah, we cannot constrain any kind of system to have symmetric matrix, right? Now, similarity of matrices. Yeah. Similar matrix. What does it mean? Can anyone interpret what is the meaning?
If A equals A equals A, some
Huh? So okay. The title says similarity of matrices. Okay. So matrix A is similar to another matrix called A hat in there. They are similar if the other matrix is obtained by coordinate transformation like this one. Okay, so the statement can be said like this: A is similar to B, let's say, if B is obtained by, yeah, for any kind of invertible P. Okay, any kind of invertible P. I'm saying any kind. Invertible matrix that has inverse. Okay.
Oh,
Invertible P means P has inverse.
or non-singular.
Non-singular. What else?
All non-singular.
All non-singular. Non-singular, and then what? Columns are linear independent, and then what else?
Rank is full.
Rank is full. Yeah, okay. All of those equivalent condition, yeah. Okay. When A is similar to B, then what's so special about similar?
It's the same.
What's the same? You can choose one. Is it the eigenvalue or the eigenfactor that's the same? The eigenvalue is the same. Okay. The eigenfactor will be different, but eigenvalue are the same. Okay. Okay. How do you see that? Yeah. Let's see this. Yeah. Okay. In this situation, lambda is eigenvalue of A. X is the eigenfactor of A. Okay. So if I say pre-multiply by P, so P times B is A times P. So and then P inverse is equal to A. Yeah. Okay. So I can replace A with this P inverse. Yeah. So I will write down that A is equal to P inverse times X lambda times X. Okay. The same, right? They are the same, right? Because I obtain A through the transformation coordinate. When B is this one, then I can write down A to be this. Yeah. Okay. No objection. Yeah. Then I will multiply the left side by P inverse, right side by P inverse. What I will get if I multiply P inverse? P inverse times P, it's gone. Yeah, it becomes P inverse X. Okay, P inverse times P become identity, right? Now we have this on the left side. On the right side, we have lambda times P inverse X. Yeah. Okay, lambda is a scalar. I can move it to the left side. So the result is that I will have P inverse X is equal to lambda P inverse X. What's the new eigenfactor? P inverse X is the eigenfactor for B, and the eigenvalue is still lambda. Yeah. Similar eigenvalue, different eigenfactor. Okay. Yeah, which is why it's called similar matrix. They have similar eigenvalues. Now we move on to diagonalization of matrix. Diagonalization of matrix means we want to make a matrix to be diagonal through a transformation. Yeah. What is the example of diagonal matrix? This one, yeah. Okay. So the original matrix is A, yeah, here. Okay. And then I will transform A using a matrix that consists of the eigenfactors. Okay, but the eigenfactors must be the basis of eigenfactors, means they have to be linear independent. Okay, So eigenvector that are linear independent, they are a basis. And so when we form the matrix based on the eigenvector, we will have invertible matrix. Is this understandable? No? Okay. Example. Yeah, pay attention. We still have 10 more minutes. Come on.
Right.
Okay, let us find the eigenvector for this. Okay, so we know that the first eigenvector, sorry, let's say this is x1, x2, this is x1, x2, yeah, because the first lambda is 1. Okay, and so we have 0x1 plus 2x2 is equal to x2, right? Correct? Yeah, I'm using the second row, second equation. Okay, 0 times x1 plus 2 times x2 is equal to x2. Okay, correct?
Okay.
And so what should be the x2? What should be the x2?
X2 out.
Huh? No, it cannot be. This is the eigenvalue of 2, yeah. Say if I use this, I will get the wait 0x2. Okay, it has to be 2 in here, yeah. To be 2 in there, x2 is equal to x2. Then in this case,
Diagonalisasi.
what 0 times x1 so x1 is free to choose, but isn't it x2 also free to choose in this case?
Yes.
Do you open MATLAB?
Oh yeah.
I'm trying to find the basis of eigenvectors in here.
I need to open my laptop first.
Okay. No need.
Belum login. Coba, tekan apa itu, Pak?
What about if we use the second one, x1 plus 3x2 equal to 1. So 2 is equal to 0. 2 must be 0. So if I have 1, finding the eigenvector. 0, 1.
Maybe.
Yes, sir. No.
Okay. Yeah. The eigenvector is just 1, 0, and 0, 1. Okay, because we have 1 times 0, 3 times 1. Sorry. It's not, yeah. No, it's not. 1 times 0, 3 times 1 equal to... No, it's not 0 and 1. What's the eigenfactor for the set? For the eigenvalue? The second eigenvalue?
Berapa kan?
Eigenvalue-nya 2.
2.
For the eigenvalue of 2, what's the eigenfactor?
Oh, eigenvector.
0 times x1 plus 2x2
X2. Second one. 0.
is equal to this. X1 is free to choose, but non-zero.
Isn't it supposed to be 0 and X2?
Sorry again.
0 and X2.
For the second one, 0. Let's try. 1, 3, 0 and add any number, right? Is it? So it should be 0 and it should be like this. 1 times 0, 3 times x2. It's 2 times 0. No, cannot. Yeah, which is why is it? Yeah, we get the first eigenfactor. What's the second one?
First one is 1 and 0.
Berapa?
Oh, sige. Kurang ngerti secara Eigenvalue-nya 1 and 2. Alah.
Then 0 plus
3 and 1. 3 and 1. Eigenvalue 1 and 2. Eigenvectornya 1, 0 sama 3, 1.
wait.
0 deh, Pak.
2, right?
Alah,
X2.
Cara taunya gimana terus?
Okay. Yeah, x2 and x1 is defined by this.
How do we find it? Like,
Okay. I supposed to use the first line. Yeah, the second line doesn't give me any answer.
So first line times the x1, x2.
Yeah. So we will have 1, 3, 0, 2. X1 is 3. This is 1. 2 times 3, 1. Okay. 1 times 3 plus 3 times 1 is 6. 0, 2, 2. Okay. So we will have the x in that case will be 1, 0 and then 3, 1. Okay. The capital X in that case will be this. Okay. So if we multiply x inverse times a times x, what was the inverse of this? Can you get the inverse?
Symmetric kan?
No. Upper triangular.
Triangular. Triangular.
Is it 1 over 3 here? So our D is
1 minus 3, 0, 1,
minus 3?
1 minus
No,
3.
you didn't say anything.
1 minus 3 minus
Ya
2.
harus cari maksudnya.
1, 3, 0, 1.
Here we minus half minus 3 over 2 minus half. Plus 3 over 2 minus half.
Okay, this is 0. Okay, I think it's this one.
Yeah.
Okay, I think 1 minus 3, 1, 0, 1. Yeah. Okay, when you multiply this, I should get a diagonal matrix which has 1, 0, 0, and 2. I should get this matrix, diagonal, which consists, the diagonal will be the eigenvalue of that matrix. Okay, let's multiply from here, yeah. 1 times 1, 1, 0.
0, 0, 2.
So I will have 1 times 3 minus 3 times 2 minus 3, 0, 1. This is 0, right? 0 and 2. Okay, what is this?
1,
1, 3, 0, 1. 1, yeah?
1, 0,
1, 3.
1,
This is 0. 0 also.
0.
This is 2. Okay. So I will get diagonal matrix.
Oh iya juga.
Yeah. Yeah, take some time to think about the eigenvector.
Oh, itu minus 3 dari mana? Bukannya jadi 3 doang ya? Determinannya 1 gak sih?
This one? I'm just multiplying this and I get identity, then I just satisfy with it.
Oh.
Ya. Kalau hasil identity berarti dia benar ya?
Yeah. Okay. With this identity, then I'm getting the correct inverse. Okay. So if your matrix has a basis eigenvectors, how do you get matrix to have a basis of eigenvectors?
Basis of eigen.
Yeah. What kind of condition?
Ya, diagonal.
You revert back to this
Be
definition,
distinct.
yeah. This definition,
Eigenvalue should be distinct.
eigenvalue distinct, or when the matrix is symmetric. Yeah.
Kalau symmetric berarti
If it is symmetric, then you can do diagonalization. Always. Symmetric matrix, always diagonalizable. If it is not symmetric, it is not always. Okay. Any issue? The Jordan block. We don't discuss the Jordan block for the exam or for your BCST, yeah. No, but for the sake of your understanding, let us discuss a bit that. After I finish this, yeah. You see that when we have D like this, then D is a similar matrix to A, yeah. Similar, right? Eigenvalue are the same. Can you see that eigenvalue of A is 1 and 2?
Yes.
What is eigenvalue of D? Also 1 and 2. Similar matrix. But they will have a different eigenvector. Okay. And then this one will also hold. Okay. If these are diagonal, then when you take the power of it, it is the same as you are taking power of A. Okay. Yeah. So we move on. That's the exercise. Now let me talk about Jordan block a bit, just a bit. An example of Jordan block is this. Yeah. What is the eigenvalue of this matrix? 0 and 0. Okay. Lambda is just 0 and also 0. What is the eigenvector? Zero, 1, 0, 0. Multiply by what? B0. Yeah, the first one free to choose. The second one has to be 0. Yeah. So I can have 1 and 0, sorry. Like this, then the result is just 0. Okay, now I have to create another eigenvector, which also results in 0. Yeah. What's the possibility? 0 and 1. 0 times 0, 1 times 1, 1. Cannot. What about 1 and 1?
0, 1.
Okay, if you have a vector like this, the only possible another eigenvector that is linear independent to this is what? Either 0, 1 or 1, 1 or 1 minus 1 lah. The one that can counter the 0 in here, yeah. Okay, but as you can see, all of this collection of vectors, it doesn't work for that. Yeah, so that's the problem with the Jordan block. Your eigenvector is not linear independent. Yeah, repeated eigenvalue with Jordan block is quite troublesome. Okay, we need the advanced discussion on this if you want to tackle the Jordan block. Not at the moment. Okay, so I will see you again on next Tuesday